Okay, so next two sections should be probably the easiest two sections we've had this year, or close to it. They're both dealing with linear functions, and double check, I did record, okay. So we're going to try to at least do both sets of notes today. We'll have one homework set over 2.4, and then tomorrow will be a work day over 2.5. So in this first section, we're looking at finding intercepts of functions, reviewing basic concepts, looking at something called average rate of change. This sounds fancy, but all this is slope. It's just a different way of looking at slope, so that's also something we've done before. And then we'll also construct linear models. So let's start off talking about intercepts. So there's two types of intercepts, x-intercepts and y-intercept. An x-intercept is any place that a function crosses the x-axis. Now, this is obviously not a linear function. Any function that crosses the x-axis, those points are called x-intercepts. And then the place where it crosses the y-intercept or the y-axis is your y-intercept. Notice the important thing is that when it's an x-intercept, the y is 0, and when it's a y-intercept, the x is 0. Now, a function can have as many x-intercepts as it wants and continue to cross the x-axis over and over. But you can only have one y-intercept. Why is that? Why can't I have two of these? Why couldn't a function do that? It wouldn't pass the vertical line test. It wouldn't be a function anymore. Now, a graph, just a general graph can do that, but it wouldn't be a function anymore. So functions can have any number of x-intercepts, but they can only have one y-intercept. Okay, so in general, this is true for any function, not just for a linear function. If you want to find the x-intercepts, the trick is to plug 0 in for y and solve for x. If you want to find the y-intercept, you plug 0 in for x and solve for y. So you simply plug in the opposite variable, plug 0 in for the opposite variable, and solve for the intercept that you want. Now, if you're using function notation, the way that we would think of it is, for x-intercepts, you're solving this equation, 0 equals f of x. You plug 0 in for y, and then you solve that for x. If you're finding the y-intercept, then you're simply plugging 0 in for x, so you just evaluate the function at 0. Okay, so linear functions. Any linear function can be expressed in this form, f of x equals ax plus b. Now, we typically think of a as m, or it's the slope. They're just using a different variable, but it's still the same concept. And the b is going to be the y-intercept. For any linear function, the domain is all real numbers. What is the domain again? No, I'm sorry. What does it mean? What does the domain mean? It's all the input values. So you're allowed to plug in anything that you want into a linear function. If a is different from 0, meaning the slope is different from 0, then the range will also be all real numbers. Right? If it has a positive slope or a negative slope, the range is going to be all real numbers. If it has 0 slope, then it's horizontal, and then it doesn't have a range of all real numbers. All right, let's go through graphing a linear function. So, real basic one here. What do we know right away just by looking at it? Okay, y-intercept is 6, and then what else do we know? All right, slope is -2, or think of it as -2 over 1. So if I'm going to graph this, where do I start? 6 on the y-axis. How do I move? Down 2 to the right 1, down 2 to the right 1, and just keep doing that. All right, and then take a straight edge and connect those points. All right, so then it says identify the domain and the range. Well, we should have been able to do this without even graphing it, but what is the domain? All real numbers, right? Linear functions, domains, all real numbers. Range, also all real numbers because the slope is not 0. I noticed I didn't actually follow the directions. The directions said to graph it just using the intercepts. So let's back up, and we did find the y-intercept. How would I find the x-intercept? Plug 0 in for y, and and solve for x. In other words, solve that equation. 0 equals negative 2x plus 6, and add the 2x over, x comes out to 3. So if we were going to graph it just using the intercepts, I would have graphed this 6 and this 3 and then just drawn it straight from there. Oftentimes it is faster to just find the intercepts and graph it from the intercepts. When we get to linear programming later on in the year, we'll see that this is the preferred way to graph a linear function because the slope gets so messy later on. Okay, let's try a different one. So we've got f of x equals negative 3. Remember that this could just be written as y equals negative 3 because f of x is y. So how do we graph this? What type of line is it? So this is a horizontal line. The y value is always negative 3. So it is just like that. What's the domain? Still all real numbers. And then range, this one is not all real numbers. So remember to do the range, you take it and smash it onto the y-axis. There's only one thing, just the number negative 3. Remember that the range is the set of all outputs. The only output that this function ever has is negative 3. This is what we call a constant function. If you plug anything into it, f of 2, output's negative 3. f of 0, output is negative 3. f of 1000, output is negative 3. It's always the same thing. The output is only this value. So it's not an interval, it's a singleton, just a single number. Yeah.
Do you have to use the little, like...
The braces, the curly braces, yes.
So you can't use the bracket?
No, so that intervals are always an infinite set of numbers, so you don't, like, doing this is not considered to be defined. So an interval always needs to have some length to it, and so for a single number, we use the braces. All right, how about this one? Notice that this one does not say graph a function, it says graph a linear relation. X equals negative 3, how does that look? It's a vertical line through negative 3. But it still has domain and range. Domain, all of the x values. What are all the possible x values for that line? Just negative 3, so just a single value. And then range, that's all real numbers. All right, questions with that one? All right, slope. So probably the most important concept when you have a line is this concept of slope. We know that slope is the change in y over change in x. So this little triangle thing you see here, if you haven't seen that symbol before, it's actually a Greek letter delta. It's capital delta. And it simply just means change. Change in y over change in x. Typically, we rewrite that as y2 minus y1 over x2 minus x1. Those differences are the respective changes. We also think of it as just rise over run. The important thing is if you have any line and you take 2 points on that line and you calculate this ratio, the change in y over the change in x, no matter where it is, that ratio will always be the same, no matter where those points are on the line. Now, we define for a vertical line, a line going straight up and down, the slope is undefined because what is the change in the x? It's nothing, right? So you'd have division by 0 with a vertical line. And if it's a horizontal line, the change in y is 0, so that slope is 0. So horizontal is 0, but vertical is undefined. Slope is a measure of steepness, so the idea is that the horizontal line here is not steep at all, so its slope should be 0, but you can't get any steeper than a vertical line. It's like infinite slope. The problem is it could be positively infinite or negatively infinite, so we just say that it's undefined. Okay, so this picture here characterizes all of those. When you're looking at slope, think about going up a hill, but we always move from left to right. So this is a positive slope, negative slope going from left to right, that's going downhill, and we already did 0 and undefined slopes. Okay, so this leads us to the concept of the average rate of change of a function. So in this graph here, I just have this blue function graph there, and we're looking at two different points, the point at A and the point at B on the function, and the idea is I want to know what's the average rate of change over this time interval. And the way to do that is you simply find the slope of that secant line. The red line that you see here is what we call a secant line. It just intersects the function at two different points. And if you find the slope between those 2 points, that is the average rate of change. So this looks like a fancy new formula, but it really is just y2 minus y1 over x2 minus x1. It's slope. So average rate of change is simply slope of the secant line. This becomes an especially important concept when you get to calculus. This idea of rate of change it's really the key thing at the beginning of calculus. Okay, so let's try an example of this first. So I think this is my own. I don't think this one's in the book. It might be. So suppose distance traveled in miles is given by the function y equals f of x, where y is distance and x is time in hours. So I wrote down here, I've got this is hours, and this is miles. So the blue curve that you see here is supposed to be simulating distance traveled. So the idea is at 2 hours we had traveled 10 miles, and at 9 hours we had traveled 486 total miles. So if we want the average rate of change, in other words, the average speed, we need to do f of b minus f of a over b minus a. In other words, the slope of that line there. In this case, b would be 9, so f of 9 minus f of 2 over 9 minus 2. It's the change in y over the change in x. Now we already know these values just from the graph. F of 9 is 486, f of 2 is 10, over the bottom would just be 7. Alright, so what we end up with is 476 over 7. Divide that out for me. Now let's think about the units on this. If you go back to the fraction, get rid of this here. This is change in y over change in x. What were the units on y and what were the units on x? I had to erase it over here, but what were the units here? These are miles, and this is hours. So the units of the final answer is miles per hour. So our average speed over those 7 hours, we averaged 68 miles per hour. Make sense? But all we really did there was slope. Let's try a different application. So we're going to do average rate of change again, but it's not going to be about speed here. So it says in 2009, Google spent $2,800 million on research and development. In 2013, they spent $8,000 million on research and development. It says assume that the relationship is linear and find the average rate of change in the amount of money spent on R&D. So I already graphed those points here. In 2009, they spent $2,800 million. In 2013, they spent $8,000 million. So if we want to know the average rate of change in the amount spent on the R&D, all we need to do is find the slope of that secant. So average rate of change in R and D spending would be change in Y, so 8,000 minus 2,800 over 2013 minus 2009. All right, so in the numerator you get 6,200. Denominator we get 4. Divide that out for me. so then what would be the units on this? What's the units on the Y? Millions of dollars. So it's not just dollars, it's millions of dollars. Per year. So the idea is over that time interval, over those 4 years, they averaged the amount they spent on R&D increased by that much every single year, $1,550 million per year. Is this okay?
You did math wrong.
Where?
8,000 minus 2,800 is 52.
Oh yeah, 5,200, you're right. Yeah, we definitely want that to be right. Okay, so what does that divide out to?
Yeah. 1,300.
1,300? 1,300?
Yeah.
All right, we good then? Okay, let's look at another application of linear models. A very common one is finance applications where you're looking for a profit equation. So profit is the amount of money that you make after you remove any costs. So the idea is the amount of money that you bring in for a product is revenue, and the amount that you have to pay to produce it is cost. And typically, those are going to be expressed as linear functions. So if we look at, this is our cost function. The slope of that, the m, represents cost per item, how much it costs to produce each of those items. And b is going to be the fixed setup cost. You know, maybe you have to rent a building or just whatever the fixed cost is to get set up. You do that, you pay that one time, but then every single item has a certain cost associated to it as well. So that's our cost function. Revenue is going to be the money that you earn from selling the product. And the idea for that is going to be, P is going to be the price that you sell it for, and then X is going to be the number that you actually sell. For our examples, we're going to keep them simple, and we're going to assume that every one that we make, we also sell. So these two variables can be the same thing. That if you make it, you are going to sell it. It's not always true, obviously, but keeps the model simple here. So then the profit function is simply revenue minus cost. Find the money you make, subtract the money that you have to pay. So let's try an example of this. It says assume that the cost to produce an item is a linear function and all items produced are sold. The fixed cost is $1,500 and variable cost per item is $100. The item sells for $125. Write functions to model each of the following. So cost function. We know that's mx plus b. What's m? What do you think? So that's the 100. That's the cost per item. Every item costs 100. So that's 100 times every item you produce. The fixed cost then is the 1,500. So that is our cost function. Revenue. We know that that is P times X, which will be the price of the item, which is 125, times X. So that is our revenue function. And then profit equals revenue minus the cost. So it is simply, let's give myself a little more room here, 125x minus, now here's where you have to be careful, this entire thing has to be in parentheses because that negative has to get distributed. And MathXL is probably going to make you simplify that, so that looks like, what, 25x minus 1,500? All right, questions with that? All right, let's try to do, oh, I guess there is one more. It says how many items must be sold for the company to make a profit? This is oftentimes called the break-even point. Where we break even. So, how do we set that up? What would it be? What would it look like if we didn't lose money and we didn't gain money? What would profit be then? When we break even, meaning cost equals revenue. Break even point is when profit is equal to 0. So we need to set that equation up. That was, profit again was 25x minus 1500. Set that equal to 0. This will give us the break even point. And then if x increases by just 1 unit, that's when we start to make a profit. So add the 1500 over, 25x equals 1500, divide the 25. All right, divide that for me. 12. So the idea is if we sell...
I thought you said 125. Sorry. Okay, 60.
60. If we sell 60 items, we don't make any money and we don't lose any money. That's the break-even point. So we need to sell 61 items to make a profit. 61 or more items. Or you could just say, must sell more than 60 items to make a profit. Questions with any of those? All right, so let's switch over to 2.5. This really should just have been one section. I think the author of the text had written different textbooks, and rather than just combine these, he kind of just put them sequentially after each other because it's really just a continuation. Okay, so in this section we're going to write linear equations in point-slope form. This is a form of a linear equation that you would have been introduced to in Algebra 1, but then they probably just hid it away because usually students prefer slope-intercept form. This is the y equals mx plus b form. When it comes to higher level courses, we usually prefer point-slope form. In calculus, we use it almost exclusively because it is just so much faster to use point-slope form. So we're going to reintroduce it here, maybe convert some of you over to that form, but probably not. We'll look at vertical and horizontal lines, which we kind of already have done, equations of parallel and perpendicular lines, and then the last two things, these will be new things, and both of them are using your graphing calculator. So we'll look at forming the line of best fit using your graphing calculator and the solution to an equation using graphing calculator. I may not do these today. We may stop here and do these two tomorrow. Okay, so let's start with point-slope form. So we're actually going to generate the formula for this equation. So the idea is I've given you a line here. We know that it has slope m. And I've just labeled two different points on the line. I'm calling the one on the left xy and the one on the right x1, y1. The way to think of this is this point here is fixed. We're not going to move that point. But this point, since it doesn't have subscripts on it, the idea is it can kind of move up and down the line. But you can think of them both as fixed. It really doesn't make a difference. So what we do is we start off by finding the slope between those 2 points. We know that slope is change in y over change in x. So I've just plugged those coordinates in. Y minus y1 over x minus x1. These could easily be switched, but it's just going to make the resulting equation look a little different. It doesn't really make, it doesn't change it, but I like this order better. So then what I did is I multiplied both sides by the denominator to get this equation, just sending that over to the left-hand side. And then I flipped the whole equation around using the symmetric property so that the y's are on the left. So this is what we call point-slope form. It is literally just the slope formula rewritten. That's all it is. Just move this to the other side. The benefit of this formula is all you have to know is the slope and a single point on the line, and you plug them directly in, and you immediately have an equation of a line. You don't have to do any extra work after that. It looks messier than just what you're used to, the y equals mx plus b, but it is actually faster to get an equation of a line in that form. So let's try doing that with this. I'll go ahead and rewrite point slope form, y minus y1 equals m times x minus x1. So then all we have to do is plug in the point. This point is x1, y1, and we plug in our slope, that's the m. So we have y minus 1 equals negative 3 times x, and then here's where you have to be careful, that's minus a negative 4. Got to be careful with your negative signs on this. So it is y minus 1 equals negative 3 times x plus 4. And that's it. It's the equation of the line. Now, it's possible that they want you to enter the equation in y equals form, that they want it in slope-intercept form, and you can easily get there from this form. This problem didn't ask for that, but if we needed to do that, we would distribute and then add 1 to the other side. So now it's in y equals form. It doesn't actually make graphing it any easier to be in this form because we already have a point. We'll see what I mean by that later on, but if it's required to get it in that form, you just solve it for y. Questions on that one? Okay, the next thing, I have a table that has all the different forms for a linear equation and what they're like, when to use them. And these are just suggestions too, but first one, we've got slope-intercept form. This is the one you're most familiar with. We know the m is the slope, the b is the y-intercept. One of the nice things about this is if you're ever graphing in a utility like your graphing calculator or maybe like an online graphing utility, they will typically always require this form. The nice thing about it is you can immediately identify the slope and the y-intercept just by looking at it. All right, the one we just went through is point slope form. This is the ideal form for finding an equation if you know the slope and you know a point. Then you can immediately just go to that form. Another form for a linear equation that you probably didn't use much last year is standard form. Standard form is where x and y are on the same side, and the constant term is on the other side. The benefit of this form is it's the easiest form to find the x and y intercepts. We'll see this much more when we get to plotting systems of equations and systems of inequalities. Then the last two are horizontal and vertical lines. We've already done these. Y equals a number is a horizontal line. X equal a number is a vertical line. Okay, so let's move on to parallel and perpendicular. So parallel lines. From geometry, you learn that parallel lines are two lines that are in the same plane that never intersect. If we think about them in terms of graphing them with equations, then how does their steepness compare? Same steepness, right? They increase at the same rate. That means that parallel lines have to have the same slope. Now, if we look at perpendicular lines, that's not very good, is it? Let's try that again. Still not good, but we can see clearly they do not have the same slope. These would have positive slope where the blue line has a negative slope. So one thing we notice right away is that they should have opposite signs, but not only do they have opposite signs, their slopes are flipped over. They're reciprocals of each other. So the slopes are negative reciprocals. So just to make sure we're clear on that, suppose that the slope of the red line is 1/3. What would be the slope of the perpendicular? I'm using that upside down T symbol for perpendicular. Careful. It'd be -3 because we have to flip it and negate it. Notice in here it says that the slopes of perpendicular lines, the product is -1. If you multiply negative reciprocals, you always get -1. Now, the other thing we should mention is it's got this non-vertical here. What would we say if you have a horizontal line and a vertical line? Their slopes are not negative reciprocals. The slope of this horizontal is, and the slope of the vertical is undefined, right? So if they're horizontal and vertical, one of them is zero slope and one of them is undefined slope. They're the only ones that don't follow this negative reciprocal. All right, let's try finding some equations then. Okay, we want the line parallel to this, passing through this point up here, 3, 5. So first thing we need to find is the slope. How am I going to get the slope of that line? Solve it for y. So we're going to subtract the 2x over. 5y equals negative 2x plus 4. Then divide by 5. Just divided both sides by 5. But on this right-hand side, we can actually split that fraction up. So it's negative 2/5 x plus 4/5. So the slope is clearly negative 2/5. And we have the point 3, 5. So now all we have to do is find that equation. I'm going to show this in two ways. My guess is most of you are going to prefer the second way. But if you have a point and you have slope, then point-slope form is usually the preferred way to go. It's just not what you are probably most comfortable with. So I put in the slope, and then I just put in the point, so it would be y minus 5 equals negative 2/5 times x minus 3. Just plug the x in for x1, the y in for y1. There's your line. Chances are MathXL is not going to take this. They want it in y equals form. So we're going to distribute through the parentheses. Y minus 5 equals negative 2/5 x plus 6/5. And then we need to add 5 over. Alright, so that's going to be 6/5 plus 25/5. So 31/5. Okay? Alright, so you remind me then, how did you do this back in Algebra 1? I'll start it for you. Well, we know one thing right away. Put the slope in, just like I did here. So y equals negative 2/5 x plus b, then what? Good. Plug the point in, just like we did over here, but you're not over here, we did not put it in x and y, we put it in x1, y1. Here, you do put it in just x and y. So 5 equals negative 2/5 times 3 plus b. Then we got 5 equals negative 6/5 plus b. Add that over. 5 plus 6 over 5 is equal to b. Notice that is the same thing that we ended up doing over here, same algebra, so it's not any easier to do this. That's 31/5 is b, but then you have to remember to actually rewrite the whole equation. So y equals negative 2 over 5x plus 31 over 5. In terms of actual steps, they really are about the same. I would say this is maybe one step shorter, but if you're comfortable with this, it will work. You can keep doing it. But one of my biggest issues is people stop here. They forget to rewrite the whole equation. Is that okay? All right, perpendicular. Is that the same line as before? It is. So we already found the slope of this line was negative 2/5. I don't want that slope anymore. I want the perpendicular slope, which would be 5 over 2. So I'm just going to do point slope for this one. Y minus y1 equals m times x minus x1. So I put in the slope. I guess I could go ahead and just put the point in too. Still point is 3/5, so 5 in for the y, 3 in for the x. And then just go through the same process again, distributing. So y minus 5 equals 5 halves x minus 15 over 2. And then add the 5 over. Did I lose a minus sign on this one? Oh, that slope is negative now, so we're good. Okay, so on this one, we've got negative 15 over 2 plus, this is 10 over 2, so negative 5 halves. So y equals 5 halves x minus 5 halves. Is this okay? All right, how much time do we have left? I think let's hold off on that for tomorrow. So I'll introduce these last two tomorrow. All right, so your assignment should already be posted. You should be able to start it there.